Today's lesson is the first lesson in our new chapter, Chapter 5. The title of the overall chapter is the definite integral, but our first lesson, Lesson 1, is just going to be simple, how to find a basic antiderivative. What's interesting is you already know the word derivative. We did that in Chapters 3 and 4, but in Chapter 5, we're going to go backwards, hence the word anti in front of it. Now, Chapter 5 is one of my favorite chapters because it builds and it builds and it builds, and then all at once everything kind of comes together. In this lesson, we're just going to be doing the skill of antidifferentiation, and I'm going to be giving you some notation that's not quite going to make sense yet, but I promise in the next few lessons over the next week it will make sense. For example, when we do our first example, example 1, I'm going to start with this elongated S shape. Now, for today's purposes, I just want you to see that S shape and say to yourself, find the antiderivative. That's going to serve the purpose for today. Eventually, you're going to get the real meaning of what this elongated S does, but for today, it's going to help me to not have to keep writing out the words, find the antiderivative, find the antiderivative. So let's just use this S symbol to signal that we're about to find an antiderivative. Now I'm going to put a function inside here. I'm going to start with the function 4x to the third power, and then behind it, I'm going to put dx. And for today, I just want you to say to yourself, when you see that dx, with respect to x. So, we're going to find the antiderivative of the function 4x to the third power with respect to the variable x. If this was a y for y to the third, then this would say dy. If this was for z to the third, this would say dz. So this variable here will change as this variable changes. Okay, now here's how easy this is. You put an equal sign, and then I'm going to put a blank to fill in our answer. So really what you're going to do is, whatever the answer is here, its derivative must be 4x to the third. So you have to think to yourself, you could even pause it right now, what function's derivative is 4x to the third? Hopefully, on some level, you're thinking x to the fourth. Because if you did the power rule on x to the fourth, of course, you would bring the 4 to the front and reduce this exponent by 1, so 4x to the third, which is right here. Now, to finish this, I'm actually going to add a constant c to the back of my answer. This is an arbitrary constant that we add to the back of all antiderivatives because the derivative of a constant is 0. So we could have, let's say the constant is x to the fourth plus 15. Well, the derivative of x to the fourth plus 15 is still 4x to the third. Or maybe we have x to the fourth minus 6. The derivative of x to the fourth minus 6 is still 4x to the third. So the true antiderivative is x to the fourth plus any old constant c. That would be true to have a derivative of 4x to the third. Okay, let's try another one. Example 2. Let's find the antiderivative of 3x to the second power with respect to x. Okay. Let's put our answer bar out here. So, what function's derivative is 3x to the second power? Well, I'm starting to notice a few things here. For example, if you look up top here, see how the 3 became a 4? I'm definitely thinking about that because when I do the power rule to take a derivative, I subtract 1 to the exponent. So when I'm going backwards, I'm thinking I'm going to add 1 to the exponent. So if I take a 2, and add 1, I'm going to get 3. So I'm thinking it has something to do with an x to the third. And if I take the derivative of x to the third, indeed, by the power rule, I get 3x to the second. So there it is. Add the constant c on the back. Okay, let's try another one. Example 3. How about the antiderivative of 5 with respect to x? Okay. So I have to think to myself, what function's derivative is just the constant 5? Well, that would just be 5x. The derivative of 5x is 5. Again, if this was dy, I would put 5y. If this was dr, I would put 5r. And then add the constant c to the back. Okay, hopefully you're getting the hang of this. Let's go on to example 4. Antiderivative of, let's do x to the 5th dx. Okay, so what function's derivative is x to the 5th? Okay, well, I'm thinking if I add 1 to the exponent, I'm going to get x to the 6th. The problem with this answer, though, is if I take the derivative of x to the 6th, I get 6x to the 5th. But this is 1x to the 5th. So I have to think, well, what would I put here in front that when I multiply by 6, I get 1? So I'm thinking 1/6. 6 times 1 over 6 is 1. Subtract 1 from the exponent, 1x to the 5th, and add that arbitrary constant c. So you can see that one was a little bit harder to see than some of the others. So I think it's about time I give you the rule. Some of us like a recipe. I'm going to give you the recipe to find any basic antiderivative with the power rule in reverse. Here's what it says. If you're taking the antiderivative of any coefficient, we'll call it a, x to the nth power with respect to x, the antiderivative will always be add 1 to the current exponent, so x to the n plus 1, and then you're going to take the a and you're going to divide it by n plus 1. So whatever the new exponent is, you're going to put that new exponent underneath the current coefficient and then add c. One thing that you have to note here is that n cannot equal -1. Because if it did, -1 plus 1 would be 0, and that would create division by 0, which we can't do. So just note that. Okay, so let's look back at this one. If we had used the rule on this one, well, we would have taken the 5, we would have added 1, so there's the n plus 1, or the 5 plus 1. Put that down a little bit, okay? And then we would take the current coefficient, 1, which is the a, and divide by this new exponent. In just really layman's terms, I just say, add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by that, so these should match right here. And the top is whatever this was. So let's try to apply the rule to the next example. Example 5. Example 5 is going to be the antiderivative of 4x to the 1/2 with respect to x. Okay, so a little more complicated because you have that 1/2 up there, but if we use our rule, it should be pretty easy. So I'm just going to take the current exponent, and I'm going to add 1. So I'm going to take 1/2 plus 1. Then I'm going to take the coefficient that's currently there and divide it by the new exponent, which is 1/2 plus 1. And then add the constant c to the back. So just cleaning this up, 1/2 plus 1 is like 1/2 plus 2/2, so 3/2. And so the front would give me 4 divided by 3/2 plus c. And then cleaning this part up, 4 divided by 3/2 is the same as 4 times 2/3. So I'm going to say 8/3. So 8/3 x to the 3/2 plus c. That's going to be my final answer. The great thing about antiderivatives is that you can check them. So if this is your final answer, if we just take the derivative, we should get back what we started with. So let's see, if we use the power rule in this from chapter 3, 3/2 times 8/3. Let's see what that is. 8/3 times 3/2. Well, these 3's will cancel, and 8 divided by 2 is 4x. And if I subtract 2/2 from 3/2, I get 1/2. And the derivative of c is 0. And you can see that's exactly what you started with right here. So you can always test your answer by taking the derivative of it and seeing if it's what you started with. Okay, let's just try a few more. Example 6. Let's do the antiderivative of x to the 3/7 power with respect to x. See, the messier they get, the more I like having the rule. So if I take my 3/7 and I add 1 to it, 3/7 plus 7/7 is 10/7. Then I take the current coefficient, which is 1, divided by this new exponent, 10/7, plus c. 1 divided by 10/7 is the same as 1 times 7/10. So my final answer, 7/10 x to the 10/7 plus c. Okay, next one, example 7, antiderivative. Let's do something like this. 3x minus 5, quantity squared dx. All right, we haven't learned an antiderivative rule that has anything to do with parentheses, squaring, none of it. The rule that we have only deals with functions like this, where you have a coefficient and then just a single x term raised to a power. So when you see something like this, at least for today, you're going to have to algebraically manipulate it so that we can use the rule that we've learned. So I'm just going to go ahead and FOIL it. So if I write this as 3x minus 5 times 3x minus 5, what I'm really taking the antiderivative of is 9x squared minus 30x plus 25 with respect to x. And if I just go term by term, using my rule, I should have my antiderivative. So let's do it. So I'm going to add 1 to this 2. So x to the 3rd. I'm going to take the 9 and divide by the new exponent. See how those match? Minus. I'm going to take my current exponent, add 1, becomes a squared. Take the current coefficient divided by that new exponent. See how they match? This one is just more intuitive. I'm going to put an x beside it. The derivative of 25x is 25, and then add my c. And then if I reduce, I've got 3x to the 3rd minus 15x squared plus 25x plus c. And that'll be my final answer. And if I take the derivative of this, I get right back to this. The only other thing I guess I'll mention today is if you have trig functions, there is really no work to do. It's more just a knowing. So for example 8, let me just put the antiderivative of something like cosine x with respect to x. Trig's a little different. We're not going to use our rule that we developed today because, again, cosine, it's trig. That rule doesn't apply to trigonometry. So this is more just a knowing. You have to look at your answer and say to yourself, what trig function's derivative is cosine x? And if you have a good memory, you know that that's sine x plus c. So that's it for basic antidifferentiation. You're going to use these rules on the homework tonight, your packet numbers 1 to 20. And those answers are also in the back of the packet. Okay, see you for the next lesson.